Sir, start ಮಾಡಿ.
Madam. Madam. Hello. Hello, madam.
ಮಾಡಿ sir.
Okay, okay, yes, madam. Good morning. Now I am teaching strength of material for diploma students. Now some of the subjects are matching with some topics are matching with civil and mechanical, and it is very essential to learn strength of materials for both civil and mechanical engineering. The other engineers also should know about it, but still very important for our mechanical and civil engineering students. Already I have discussed. This is my 6th class. Till now, I have covered simple stress and strain. Now, just today I am concluding those classes, and I will go in with the next chapter, that is centroid and moment of inertia. I will discuss about the next 1 hour. Now, if you go ahead with now this is the basic strength of materials. Can you see this? The basics of strength of materials. It is, stress, strain, Young's modulus, shear stress, shear strain, and shear modulus. Now, already I have discussed number of times. Number of times I have discussed about this. We know all these things. That is stress strain, Young's modulus, shear stress, shear strain, shear modulus, and also we have discussed bars of varying cross section. Now this is we have discussed in length, and also we have discussed lateral strain and Poisson's ratio, and also we have discussed about the compound bars or composite sections, and also we have discussed the bulk modulus. I think my dear students, please remember we have discussed about the 4 constants. That is elastic constant. The one elastic constant is Young's modulus, shear modulus, bulk modulus, and also Poisson's ratio. There are 4 elastic constants. Now, sometimes it will be asked in the examination for 5 marks. Sometimes it will be asked for 8 marks in the examination. Please mention the elastic constants. Now, these are the 4 elastic constants. Now, all these are working. All these are definitions within the elastic limit. They are good within the elastic limit. Now, beyond the elastic limit, the body gets into plastic state. Isn't it? It is a permanent deformation. And also, we have discussed about that EGK relationship. I think you may be knowing about this. We have discussed and we have solved many number of problems with this. And also discussed about the strain energy and resilience, modulus of resilience, how to calculate it, and we have solved. There are some problems, few problems are solved in the previous classes, and some problems I have highlighted here, I have mentioned here. Now, kindly go through these problems and solve these problems. Definitely in the examination you will get 2 or 3. problems in your examination. Now, if you learn this simple stress and strain, now definitely you can score more than 50% of your strength of materials, whatever the mark allotted. But because if you don't know the simple stress and strain, we cannot handle many more other chapters. We need to understand, very carefully, and we must. You please go through this and calculate. Now these are the some examples. Now they are with me, and please kindly go through these problems and solve these problems. There are number of problems available in the various textbooks also. Textbooks are question papers. Now you must read the textbook, whatever may be our teaching, at what extent we may be teaching with you, that we are discussing in the classroom. Apart from this, you need to study the textbook. You must go through the textbook. One textbook is called Ramamrita. This is one of the best book available. And also there are many other books. Now for our level, I think this is more than we have one more Purmi is also there. You can go through this. There are a number of textbooks available in for strength of materials. Now they see this is a related problem. The questions. Now there are, I think there are 40 questions I have highlighted here. Some of them are solved in the previous class. If you go through the previous class, you can refer it. And these are the various problems we have in our stock. Please kindly go through these. It is after the class you can go through the your DT Studio. You can download and you can solve. I think you have been already. You might have gone through these things. You may be knowing. And these are the various problems available with us. You please kindly go through this, and these are many more. Whatever I highlighted, they are related to all those areas, all those. We have the problem. We have problems here. You can go through this. And then when you find time before going to the examination, you solve all these problems. Isn't it? These are the problems available. Now, I think many more problems available with the different textbooks and other things. Now we will come to the second part of the strength of material. This is for mechanical engineers, and for civil engineers this is the third part. There is one engineering mechanics. There is one part, small part is there in engineering mechanics. And the second part is simple stress and strain, and the third part is central. And for mechanical engineers, I think this is the second part. Isn't that? Now we need to understand what is the centroid, what is the relevance, what is the necessity of understanding this. Why we need to do this? Now, because whenever see we are dealing with two things: strength of materials. Strength of materials. Material strength you may be knowing. We can calculate. What is the strength of material? The material may be copper, material may be steel, material may be reinforced concrete, material may be wood, material may be aluminium, whatever may be, which are being used in our engineering practices. Isn't it? And therefore, whenever you use the material, we need to understand how the load is applied, at what point the load should be applied. Isn't it? For example, let us assume that this is one section, cross section of the material. Isn't it? Let us assume that there is a column section, that is steel column section. Now, where you have to apply the load, exactly, it is always assumed that the load is applied at the center. Isn't it? Now, suppose if you apply the force in either this side or this side, wherever you apply other than the center, there will behavior of the material is different. If you apply the load, it is assumed that the load is applied at the center. Therefore, we need to calculate the centroid of the given section for the given material. Isn't it? Now, therefore, there are two things here. One is centroid, the other one is center of gravity. The centroid, suppose if you take the section, if you crunch this, if you shrink this section, exactly it will coincide with a particular point. That point is called centroid. Isn't it? Now, when you know the mass of this plane figure is acting to a point, particular point. That point is called center of gravity. The difference between the centroid and center of gravity. When you take the material section, the plane figure, plane section, and shrink it. If you shrink this from all the end, from all the sides, if you shrink it from all the sides, it will merge at this point. Now that point is called centroid. Isn't it? Center of gravity is mass of the section is acting to a this point. Now that it is called center of gravity, isn't it? Now there are different sections are being used in our engineering practice. The most important that is one. Now this is triangular section, square section, and other sections we are using regularly. Now this is a rectangular section. This is I section, T section, and L section. Also, we have so many other sections we have. It is a channel section. It is T section again reversed, double angle, isn't it? And the circular section. There are many other sections also. No. Strictly speaking, we are able to calculate the centroid of this figure, isn't it? If we join the diagonals, then we get the centroid, this point, isn't it? Now, similarly, it is possible we can calculate the centroid of this figure also, isn't it? If we join the diagonal, it is possible we can calculate the centroid. Now, whereas here, now it is little difficult to calculate the centroid. Now, we should know, we have to understand how to calculate the centroid of this kind of section, different types of sections. If it is a rectangle, circular, or any regular section, it is possible we can find out very easily. Now we are engineers, we should know how to calculate the centroid of the given other sections, isn't it? Right? Sometimes the centroid is acting within the material, within the section, plane figure, within the figure. Sometimes the centroid of this figure is beyond the material, isn't it? Outside the section, isn't it? Therefore, we should know very carefully. We have to understand these things, isn't it? Now, already I told you that there are two things we should remember. One is the material. Which material is being used? Number one, material. The other one is property. It is called geometrical property. Geometry of the material. Geometry means size, shape factor, isn't it? Shape. Which shape is more suitable than that? I will give you the best example for that, isn't it? I will give one best example. I think you have seen this material. You know what is this? It is a metal scale, isn't it? It is a metal scale, right? You may be seeing the bridges. You may be seeing the axle of your vehicle, isn't it? There are two wheels connected by these two wheels is an axle, isn't it? How this axle has been placed, or a beam in the building. Now, normally, how they will keep it? Now, let us understand. Now, let us see. Now, this is a section. This is where there is a thickness here, isn't it? And also the length. It is a three-dimensional figure, isn't it? Three-dimensional material, right? How do you keep this up? Which is the best way? Now, therefore, the number one, the first one. See, suppose if you keep the beam and apply the force, what is going to happen? Deformation, isn't it? The same material, I will keep it like this. What is going to happen? What is going to happen? The deformation will be less, isn't it? When compared to this. Therefore, listen, metal is same, no? Material is same. Section is also same. Therefore, it plays a very big role. How you will keep this? No, therefore, now here, shape of the material, shape of the section material is very important, isn't it? No, those who know about all these things, they are not engineers. They are capable of understanding it. And got it? Now, once again, I will tell you, if you keep the material beam like this, now what is going to happen? No, it happens. If you apply the force, the same material, if you keep like this, the behavior of the material is different. Now, if you keep the material like this resists more force, isn't it? The same material, if you keep like this, it will resist the less force, isn't it? Same material, same section. Now, therefore, this plays a very big role, isn't it? Now, similarly, let us assume that it is a column, isn't it? It is a column, an RCC column or a steel column, whatever may be. If you apply the force in this direction, what is going to happen? Deformation will be, moment will be more, isn't it? If we apply the force in this direction, what is going to happen? Again, same material, same section, but the direction. Therefore, if you see a construction site around in Mangalore or wherever you go, in different sites, the column sizes are different, isn't it? The column sizes are different. One column is kept like this, the other column is kept like this. Now, understand now? Do you understand this now? Why they are keeping the columns in the different directions? Isn't it? Because if you keep the column like this, it will deform more, isn't it? If you keep the column like this, the deformation will be less, isn't it? Now, depending upon the load received, isn't it? Load transferred, the column size will be decided, isn't it? Even while designing the tower also, keeping this, isn't it? Keeping this column or the load resisting member, if you look at the auditorium of our KPT Mangalore auditorium, there is a truss. Have you seen the truss? The truss is made out of steel angles. That is angle section. It is made out of this section, right? Now this section, it is fashioned in such a way that the deformation should be less, isn't it? Therefore, now this chapter gives where load is to be applied, isn't it? Right? Now again, I will come back little later after completing this centroid, and now when you go to the moment of inertia, I will discuss once again about this scale or this column, isn't it? This load resisting element, isn't it? Now therefore, now we will go to the next. Now these are the various sections are being used in our engineering practice, isn't it? Now therefore, how to calculate the centroid? How to calculate the centroid of a given figure? How to calculate the centroid of the given figure? The centroid of the given figure can be calculated any shape, whatever may be the shape of the material, isn't it? Or section. A plane figure. A plane figure. No, for example, let us take one irregular figure, isn't it? How to calculate the centroid of this irregular figure, isn't it? When you see to calculate the centroid of figure, what we should do, what we have to do. First what we should do. Now we have to divide this figure into a number of parts, isn't it? Now, instead of calculating the area of this figure, now it is very easy to calculate the area of this strip, isn't it? It is almost like a rectangle, isn't it? The error will be less, isn't it? Now, therefore, see, this behaves like a triangle, this behaves like a trapezoid. See, different, very easy to calculate the area of each strip. It is very easy and simple to calculate the area. Now, therefore, when you are able to calculate the area easily, now we can calculate. Now, see, for example, now always please remember that now this is the x-axis and y-axis. And one more thing, the most important thing you should remember one is now what now for example, now this is the centroid. Now come and tell me where it is lying. Center, isn't it? Okay. Now where it is lying? Where it is lying? How do you say that? Now you want to convey this message to your close friend sitting in America. He is designing it. How do you tell him that? There is no communication. Now you have to speak to him over phone. How do you say that the centroid is here? Then therefore always the centroid will be mentioned with respect to reference, isn't it? With respect to reference, isn't it? With respect to reference, when you discuss the reference, our system is more acquainted with x and y axis, isn't it? X axis, y axis, isn't it? X axis, y axis. It is more suitable for our communication system, isn't it? Even your computer, if you are handling the AutoCAD, if you open the AutoCAD, your AutoCAD is also working with respect to axis. When you open your AutoCAD, you will see in the monitor, there is at the left bottom side, you can see one x-axis, y-axis, the other one is z-axis. You can see that, isn't it? Now, similarly, if you If you observe, just below that, just below that axis symbol, there is a one X, one Y, and the other one is Z. When you move your cursor, the X, Y, Z will be automatically change its position, isn't it? Therefore, the code it is a coordinate system, isn't it? Coordinate system, that is one point to other point. Automatically, it will calculate the area, isn't it? Sorry, distance. Whatever you want, we can calculate it. Not that is more suitable for our world system in the entire world system. Now, therefore, we will adopt. Let us adopt x-axis, y-axis, isn't it? X-axis, y-axis. With respect to, now I will tell you. Now see, this is I will take this as a reference axis, isn't it? This is I will take the reference axis with respect to this axis, reference axis at a distance y bar, isn't it? With reference to this vertical axis, this is with respect to this. From here to here, the centroid of this figure is lying at a distance, lying with respect to with this reference, it is y bar. With reference to this, it is x bar, isn't it? Not necessarily be from this point, isn't it? Now, for example, I will tell you. Now there is an object here. Now this is an object. Where it is lying? Where it is lying? Now, if you consider, see this wall is x plane, isn't it? That is y plane, and this ground is z plane, isn't it? Three mutually perpendicular axes. If you ask me where it is lying, now at this point, now I will say from the x plane 1 meter, 1.5 meter. From y plane it is 3 meter, isn't it? From z plane it is 1.5 meter, isn't it? Then everybody will understand where it is lying. Where the person who is your classmate, or your friend is sitting in America, Dubai, wherever he sits, he can say, you will understand. Oh, yes, it is lying. If this is the position of the object. I think you have studied in the first year drawing, isn't it? That is projection, isn't it? That you have studied. Now, therefore, for engineers, always you must understand the reference. Reference is more important, isn't it? Always we will discuss. Now, see 1, 2, 3, 4, 5. Where it starts from? It comes from 0. 0 is our reference, isn't it? If you go upward, it is plus. If you go downward, it becomes minus, isn't it? If you go rightward, it is. If you consider rightward plus, leftward, isn't it? It is our common sense. Now we have to adopt that. And another thing you please remember is that you are the dictator. You are the engineers. You should tell me which is plus and which is minus, isn't it? Now we can say, if somebody says this is plus, this is 0, 1 plus I will take. The other fellow, no, when you take this plus, the other side will become minus, isn't it? The other fellow is there, one more your friend, he says, no, I will take plus, and this is minus. It is isn't it? Your authority. But the universal practice is 0 plus 0 minus, isn't it? The reference plus reference minus. Universal practice, isn't it? It is up to you. You decide it, but you have to carry the same thing and for the entire problem solution, isn't it? Okay. Next up. Now, divide this figure and calculate the area, and it's very easy to find out the centroid of each these 1, 2, 3, 4 centroid of this. Now, let us calculate the moment, isn't it? Moment of area. This area moment. Area multiplied by distance. It is x1 multiplied by x1, isn't it? So similarly, area 2 multiplied by x2, area 3 multiplied by x3, isn't it? Like any number of divisions, any number of steps, you make it any number of steps. According to your convenience. Better always to make more number of steps. If you make more number of steps, you will get better result, isn't it? Better result. Okay. And similarly, now this is x-axis. Now how you are going to do it? Now let me take the moment of all these strips. This is moment area about with respect to y-axis. With respect to y-axis. If you take the with respect to y-axis, now see these are the areas. These are the moments of the area. area into x1 plus area into x2 plus area into x3 plus etc. An, isn't it? Now the T is equal to the no, each strip has the centroid, each strip has the centroid, and the entire figure is also has a one centroid, isn't it? Now therefore the moment area of each strip, sum of the moment area of each strip is equal to moment area of the entire figure, isn't it? Therefore, see the x bar is the moment, x bar is the centroid, x bar is the centroid of this figure. Somewhere here, do this from here to here it is x bar, isn't it? X bar. If from here to here it is x bar, then area of this total area and this strip area A1, A2, A3, etc. Like you sum up the moment area of all these strips and equate it to the x bar into the total area, isn't it? Now therefore after doing this, now x bar is equal to, that is, isn't it? The x1, now send this A downward, then you will get, now it is possible we can calculate the, isn't it? X bar, what is the distance of the centroid from this reference to here, centroid. Now similarly we can calculate in the y direction also, isn't it? Now therefore, now this is the outcome, this is how we can calculate it. Now let us solve a few problems, we will see, we will go through that, isn't it? See now, locate the centroid of an equal angle, isn't it? Equal angle, please remember the equal angle means, now always, see 6 mm multiplied by 6 mm multiplied by 20 mm, isn't it? 6 mm, there is overall dimension. First dimension, second dimension. First dimension 6 mm, second dimension 6 mm, and the thickness of each is 20 mm, 20 mm, isn't it? Now this is what they have given. Now let us calculate the centroid of this figure. Centroid of this figure. How do you calculate the centroid of this figure? To calculate the centroid of this figure, see first, now this is area 1, this is the section, divide this section, divide this L section, angle section into two rectangles, isn't it? This is one rectangle, the other one is the another rectangle. No, not necessarily be that in this way you have to divide, isn't it? According to your convenience, you can divide this figure into this, like this also, you can divide this area also can be, you can take this, isn't it? According to your convenience, you do it. Now this is the section 1, rectangle, section 2, rectangle. Now therefore, now calculate the area A1 is equal to 20 into, now always remember in solving the these problems, see, moment of centroid and moment of inertia, you please adopt this type, that is first always dimension, it is 20, 60, 20, 60, that is the area. Similarly, A2, this is 40 into 20, isn't it? 40 into, I think there is some error here in this, you please make a correction. No, this is 40 into 20. Now this is the way out, this is the best way to adapt, isn't it? Now it is easy to calculate the centroid of this figure, isn't it? Just join the diagonal or straight away we can calculate. This is the half of this, isn't it? 60 divided by 2. That is the centroid, that is CG1, center of gravity of the figure 1 is this point, isn't it? Similarly, this is the center of gravity of the figure 2, isn't it? This is half of this. Depth is 20, therefore half is, isn't it? 10. Now that is how we can calculate it. There is some correction here. Please make a note of this. Now, okay. Now straight away you can submit, isn't it? Straight away you can submit to the relationship which is already we have derived. That is x bar is equal to sigma x. We have two sections here. A1 x1 plus A2 x2, right? Isn't it? Similarly, now solve this, we will get that. It is the 22 millimeter. Now similarly, to locate the centroid, taking moment from x-axis. No, similarly in the other direction, isn't it? Other direction, sigma ay by sigma a1 y1 plus a1 a2 y2 divided by total area. Now that gives you 22 millimeter. Therefore, see now this is the reference. The reference is now with respect to this is the reference. This we are the reference. Now from here to here it is 20. I think that is 20 now. Yeah, 22 millimeter. Now it is a equal angle. It is the equal angle. The 22 mm. That is separated. This is y-axis and this is the x-axis. Therefore, somewhere here we will get the center of gravity. Now, for example, now I will write this. Now you please note. Now exactly. Now we must. So there is some missing in the PowerPoint. You please make a correction. See, this is the diagram given. This is the section, given section. See, so this is y-axis, this is the x-axis. X-axis. Now this is a reference. This is OA and this is OB. With respect to this, see, with respect to this, now this is the x bar. This is x bar and this is the y bar. Y bar. Now strictly speaking, now this is centroid of the given section. This is the center of gravity. Now this is x bar. Now what we have calculated, it is 22 millimeter and this is also 22 millimeter. Isn't it? Now that is the end of the problem, isn't it? Now see, if the overall dimension, this is the overall dimension, this is 60 millimeter. 60 millimeter and this is 60 millimeter. This is the overall dimension, 60 millimeter. And this is 20. I section always mentioned in the fashion. Now what is this problem given? This 20 millimeter. 20 millimeter. That is the end of the story of this problem. Normally it will be asked in the examination for 5 or 7 marks. Usually they will ask. Let's have one more problem. Let's see. We'll go through this. Okay. This is another problem. Is it second problem? Yeah. Now let me solve this in the board. I will tell you how to do that exactly. I will solve this problem. Isn't it? Centroid. Locate the centroid of unequal angle. Unequal angle. How to calculate the centroid of an unequal angle? Unequal angle means that is leg and base. Leg and base. Isn't it? One is 80 millimeter. The other one is 60 millimeter. Isn't it? Now see, now this is how the section is given. Now this is the leg. This is the leg and the base. Now this is 60. It is given that it is 60 millimeter and this is the 80. 80 they have given 80 millimeter and this is the thickness is 20 millimeter. 20 millimeter and this is also 20 millimeter. 20 millimeter. Let us assume that this is the y-axis, centroidal y-axis of the angle. Y-axis. This is y-axis, and this is the x-axis. This is the x-axis. X-axis. This is centroid. Center of gravity of the figure. This center of gravity. Now this is the x bar. This is x bar, and this is the y bar. This is y bar. Now let us calculate how to do this. Now let me divide this figure into 2 pieces like this. This is section 1. This is section 2. Now we know that is x bar is equal to sigma ax divided by sigma a is equal to a1 x1 plus a2 x2 divided by a1 plus a1 plus a. Now straight away substitute it is equal to see 20 multiplied by 60. 20 multiplied by 60. 20 multiplied by 60. Where it is, the centroid of this is acting x bar. Now from here to here. Now this is the centroid. Now this is the centroid. Isn't it? Now therefore, how much you will take? This is x1. X1. It is x1. X1 is how much here? It is 10. Therefore 10. Plus the A2. Now you take this second figure. Isn't it? 60 multiplied by 20. Therefore 60 multiplied by 20. Now where it is? Now again you find out the centroid of the section 2. Centroid of the section 2 is this is the centroid of the section 2. Therefore x2 is this. This is the x2. This is x2. Isn't it? x2 is equal to how much here now? It is 30. Isn't it? It is 30 divided by now a1. A1 is equal to 20 into 60 plus 60 into 20. That is the end of the, isn't it? That is the sigma A. Similarly, we can calculate that is x bar, y bar. Now y bar is equal to same thing, the similar kind. It is sigma AY divided by sigma A. Therefore, is equal to sigma, it is A1 Y1 plus A2 Y2 divided by A1 plus A2 is equal to, substitute the values, it is 20 into 60, 20 into 60, 20 multiplied by 60. Isn't it? It is y bar. Isn't it? Y bar. Therefore, we are calculating the y bar. Therefore, from here, this is the reference axis. This is O A. O A is the reference axis, and O B is the reference axis. Isn't it? With respect to, now therefore, now see y1. Y1 is there. From y1 is from here to here. This is y1. Y1 is how much coming? Y1 is equal to half of this 30 plus 20. Isn't it? Therefore, it becomes how much? 50. It becomes 50. 50 plus the. We will take the second figure. So this is 60 multiplied by 20. 60 multiplied by 20 divided by, sorry, no, into where it is y2. Right? It is y2. Centroid from here to here. It is y2. Y2. The y2 is equal to 10. The whole thing is divided by, it is 20 into 60 plus 60 into 20. Isn't that? That is the end of the story. This is how we can calculate the centroid. Isn't it? Now straight away we can write the answer. See where the centroid is located? Centroid is located at a distance y bar, x bar from y axis. Isn't it? And x bar from, isn't it? Understood? Right now? So similarly, now there is, I think we have one more problem that you can solve yourself. Now see, this is the angle section, one more, isn't it? Then similarly, we have one more, yeah, T section, isn't it? Now I will solve this problem also. That is to locate the centroid. Locate the centroid. To locate the centroid of T section. This is, there are two rectangular sections. One is the flange, the other one is web. One is the flange, the other one is web. There are two sections. Now how to calculate the centroid of this figure? Now see, I will write down and I will calculate it and I will explain how to do this, how to solve this problem. See, now this is the top flange. It is the flange. What is the dimension of this? It is 80 millimeter, 80 millimeter and 20 millimeter. It is 20 millimeter. Isn't it? 20 mm. And similarly, web is also, it is 60. It is 60 by 20. Now we need to calculate the centroid for this figure. Isn't it? This is 60 mm. 60, right? and this is 20. How to calculate the centroid? It is 20 millimeter. Now again, now this is the centroid. This is centroidal YY axis. Centroidal YY axis. And this is the centroidal XX axis. We don't know where it is lying. Then we change little later after calculating the value. Isn't it? After calculating this. Now this is the centroidal. Let us assume that the centroidal XX axis. Isn't it? Now where it is lying now? The centroid is lying where? The centroid of the T section. Isn't it? Where it is lying? Now it is lying with respect to, see, now I will take the reference. This is the reference. This is I will take the reference like this. See, now this is the reference. This is OA. This is the reference OA, and this is the reference OB. Now the centroid is lying with respect to OB at a distance x bar. Centroid is at a distance x bar from OB. Isn't it? Similarly, this is y bar from OA. Y bar from OA. Isn't it? Understood? So not necessarily this is OA and OB in the reference. Definitely it is possible we can calculate the reference from this point. Definitely it is possible we can calculate from 2 meter away. Isn't it? But reference from where we are calculating the moment of centroid. Now, strictly speaking, the moment centroid is calculated with respect to some reference. Isn't it? Some reference. Now this is the reference. This is OA and OB. And the other thing you must remember here, now X bar. Anybody can say where it is lying? Now let us check this. Isn't it? No, yeah, you are right. I will come to that point. Now see, this is the section 1, this is the section 2. Section 2. Now this has a centroid, and this also has a centroid. This is the centroid. Now from here to where it is x1. Isn't it? From here to where it is x1. And from here to this also has a centroid. The section 2 is also has a centroid. Isn't it? Now this is x2. X2. Isn't it? The section 1 also has a centroid. The centroid is lying at a distance x1 from OB. The section 2 has also has a centroid. It is lying at a distance x2 from OB. Isn't it? Same distance. x1, x2 are same distance. So it means that the given section is symmetrical. The given section is symmetrical. Symmetrical about that is more important. About y by axis. Given section is symmetrical about y by axis. Isn't it? Therefore, x bar is equal to how much? X bar is equal to 40 millimeter. How you are arrived at 80 divided by 2. Isn't it? That is 40 millimeter. Okay. Not necessary to calculate it. If you calculate it also, you will get the same answer. Isn't it? Now let us check how is it possible. Is it right? Now therefore, we know that x bar is equal to sigma ax divided by sigma a. Therefore, a1 x1 plus a2 x2 divided by a1 plus a. Isn't it? Now let us substitute it. Isn't it? Now see, 80 multiplied by 20 area. 80 multiplied by 20. Well, it is x1 is 40. It is 40, isn't it? 40 plus similarly that is 20 by 60, isn't it? 20 mm by 60 mm, and again where it is lying again The centroid of the second section is lying at a distance x2. x2 is equal to how much? x2 is also 40 millimeter. Isn't that 40? 40 divided by this is area A1. A1 is equal to 18 multiplied by 20 plus 20 multiplied by 60. Isn't that? That gives how much? Isn't it? It should give 40 millimeter. 40 millimeter. Isn't it? Now similarly to calculate the y bar, how do you calculate the y bar? To calculate the y bar, see y bar is equal to y bar sigma ay divided by sigma a. This is equal to a1 plus a2, a1 plus a1 into a1 into y1 plus a2 into y2 divided by a1 plus a2. Let us substitute it from a1 80 into 20, 80 by 20, 80 multiplied by 20. y1 is how much? Come on, tell me. y1. See, this is the reference. With respect to this reference, we are calculating the moment of centroid of this figure, isn't it? Therefore, y1 from here to here, centroid from here to here, reference. This is y1. Come on, tell me y1 is how much? 60 plus 10 is equal to 70 plus again, that is area A2 20 multiplied by 60, 20 multiplied by 60, 20 multiplied by 60. Where it is lying? The centroid of the second figure is lying where? From here to here. This is y2. No, from here to here. It is y2. y2 is 30. Isn't it? Divided by area 80 into 20 plus 20 into 60. 20 into 60. Isn't that 20 into 60? Okay. Now you just calculate this. Now let us calculate how much you are going to get it here. Is there a solution in our PowerPoint? Y bar. Do you have 52.8? Therefore, our assumption is right. Isn't it? You please check this. Find out. No, 52.8. 52.85. 52.85 millimeter is the answer for this y bar. Y bar is equal to. Isn't it? Therefore, now you tell me the centroid of this figure. Our assumption is right. It is less than 60. Therefore, it is below. Isn't it? Alright. Now you just check. Once again, you have to check this. Now, yeah. Once again, you check this answer. Now, kindly check this. And suppose if the answer is wrong here, maybe if the y bar is more than 60, our centroid shift to this point. Isn't it? Y bar is less than 60, then our assumption is right. Isn't it? Otherwise, you have to change that after your calculation. You just go through once again and find out. Isn't it? Okay. This is how we can calculate the centroid. There are so many other problems are also there. You find out and check with them. Isn't it? Then see, this is one more problem. Yeah. I section. Isn't it? Now here we have two sections here. Now here we have three sections. Top flange, web, and bottom flange. Isn't it? Bottom flange. Top flange, web, and bottom flange. Isn't it? There are three sections here. The same thing will continue in a similar manner. Now find out the area. That is, first locate. See, now you must go through this. First take the reference. This is the reference. Now this is, draw the figure. First write down the y-axis and x-axis, centroidal axis. These are called centroidal axis. X centroidal axis. Y is the centroid. Centroidal axis of what? Centroidal axis of y section. Isn't it? This is the centroidal axis of This is the centroid. This is the centroid of the section 1. Isn't it? Section 1. Centroid. This is the centroid of the section 1. And the respective axis, x-axis and y-axis, are the centroidal axis of section 1. Isn't it? Now, similarly, for this also, it has the second figure, that is web, also has a x-axis and y-axis. X-axis, y-axis, that is centroidal x-axis and y-axis of figure 2. Similarly, we have a centroidal axis for the figure 3 also, isn't it? And also we have a centroidal axis for the section. How many centroidal axes are there now? Yeah, there are 4. One x-axis for this section 1. 2, we have the section x-axis. We have the x-axis, and we have the x-axis for the entire figure, isn't it? There are 4 x-axis, and similarly we have the 4 y-axis. Is it right? We have the 4 axes, really right? We have this one has the y-axis, section 1 has y-axis, and section 2 also y-axis, section 3 also y-axis, and the I section also has y-axis. Now, fortunately, to reduce our work burden, all these are in the same line. Therefore, it is understood that the given section is symmetrical about y-axis, isn't it? The given section is symmetrical. Symmetrical about what? Y-axis, isn't it? Right? Y-axis. Therefore, now from wherever you take the reference, now I have taken the reference. This is X, OA, and this is the reference OB. Isn't it? Now you OA and OB. OA and OB is the reference axis. OA is the axis parallel to x-axis. OB is the axis parallel to y-axis, isn't it? Not necessarily be the your OA and OB from this point. You can consider according to your convenience, isn't it? According to your, you can draw OA. This is OB, and this is this line you can take as OA. This line we can take it as OB. No, your X bar is from here to here. Your Y bar is from here to here. Isn't it? Understood? Got it? Right now? And the other thing you should remember here, the most important thing you should remember, and it is useful for our next topic, that is next section. Now that is, now please tell me, please understand. Once again, I will repeat. Section 1 has x-axis, section 2 has x-axis, section 3 has x-axis, isn't it? Section 1 has y-axis, 2 has y-axis, similarly, and also we have the y-axis and x-axis for the y-axis, isn't it? Understood? Please remember this. And you know, please note down, is there any difference from the x-axis of the figure 1 to the x-axis of the entire figure? Is there any from here to here? Are we able to calculate the distance? From centroidal x-axis, centroidal x-axis of the figure 1, centroidal x-axis of the entire section, isn't it? Now, similarly, can we measure the distance that is between x-axis of the figure 2 and x-axis of the I sections? Similarly, can we calculate? Are we able to calculate the x-axis of the distance between the x-axis of the figure 3 and x-axis of the I section? Isn't it? Now, therefore, see, from x-axis, this is the x-axis, from here to here one distance, and this is the x-axis, and this is from here to here there is a one distance. We will discuss it briefly later. I got it. Now, fortunately, already I told you that the y-axis of all the 4 figures, there are 4 figures, 4 sections are one section here. There are four sections. Section 1, section 2, section 3, and also we have the all the four sections YY axis lying in the same line. Therefore, the given section is symmetrical, isn't it? So, therefore, from this reference, this is OA, OB, this is X bar, from here to here it is X bar, from here to here it is X bar, and from OB, OA to the centroid, this centroid, it is Y bar, isn't it? We have written here now, I think we need Y bar, and this is X bar. X bar, where it is X bar? This is X bar, isn't it? Right? Now, how to calculate this? Now, I think this problem has been, we have solved this problem. You just go through this solution. See, here 60 into 20, A2 1, right? A2 is 20 into 60, and A3 is 80 into 20, isn't it? Same figure, you know. Now, similarly, that is X bar is equal to sigma AX by sigma A, that is A1 X1, A2 X2, A3 X3. Substitute the values, that is 1200 multiplied by 40, that is X1. X1 is 40 from OB, it is 40 now. Am I right? It is 40. And similarly, 1200, area of this section 2 is 1200 multiplied by, this is again from here to here it is, isn't it? Right? From here to here, X2, this is again 40, and section 3, it is 80, 20, 1600, and the X3 is from here to the centroid, reference to the centroid is X3, isn't it? X3, and this is the area 1, area 2, area 3, and this is the answer, isn't it? Therefore, X bar is equal to how much now? X bar is equal to 40 millimeter, isn't it? Straight away, straight answer, isn't it? So similarly, now this is the Y bar. This is Y bar. From here, how do you calculate the Y bar? In a similar manner, it is A1 Y1 plus A2 Y2 plus A3 Y3. A1, area 1, and this is Y1, isn't it? From the reference axis. Remember this? Y1 is from the reference axis to the centroidal x-axis of the figure 1, isn't it? And this Y2 is the distance from the reference axis to the centroidal x-axis of the figure 2. X-axis, centroidal x-axis of the figure 2. Similarly, now this is X3, Y3. Y3 is the distance from reference to the centroidal x axis of the figure 3. Isn't it? Understood? Right? Now, therefore, now substitute the values and we got 46 millimeter. Okay? Understood? Now we'll go next again. We'll go to the next one. Now this is the moment of inertia. Moment of inertia. Right? Moment of inertia. Moment of inertia. Now, I think we have understood very clearly the centroid, isn't it? Moment of inertia. Now, already I told you that the inertia, it is the inertia force induced. Inertia force induced because of its shape. Because of its shape, isn't it? Section. There is a section. We are dealing with the section, isn't it? This is called the secondary moment of the figure. Secondary, we know that moment is equal to force into perpendicular distance, isn't it? Moment, and we know how to calculate the moment, isn't it? Force into perpendicular distance. Now, secondary moment of the figure, isn't it? This moment of inertia. This is the inertia force induced in the material section to resist the force. See, now let us assume that now this is the beam. Do you agree with this? Maybe wheel axle, maybe RCC beam, maybe steel beam, whatever maybe. Do you agree? It is a beam, isn't it? It is a three-dimensional figure, isn't it? Material. One, we have the width, we have the depth, and the length. We have three dimensions, isn't it? And if you cut this, there are number of sections. There are number of sections, isn't it? There are number of sections. Now the sections are like this. Now let us assume that this is one section, square, rectangle, isn't it? This is another rectangle, and one more rectangle, one more rectangle, one more rectangle. That is how this has been arranged. Do you agree? Do you agree with this? There is a section, rectangular section. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you agree? Right? Isn't it? The sections have been arranged. Then it becomes the beam. Right? It is the theoretical part. Theory I am discussing about now. Beam theory. Isn't it? I will come to the moment of inertia. Right? Section. Number of sections are arranged. Isn't it? Now this forms the material, isn't it? This forms the section. Understood? Right now, moment of inertia. I will come to the moment of inertia. Isn't it? See, already I told you that when you keep the member like this, what is going to happen? It resists less force. It resists less force. If you keep the member like this, it resists more force, isn't it? This is one way of saying. The other way, if you keep the member like this becomes more. Deflection will be more, isn't it? If you keep the beam like this, member like this, isn't it? Understood? Right? Isn't it? When you apply the force, when you apply the see, for example, if you take the beam, it is a beam, and there is a load on this. When you apply the force, the load is transferred from beam to the support. Isn't it? Beam to support. Wheel axle, isn't it? Wheel axle, chassis, and vehicle, isn't it? Number of goods, go, etc. It is loaded. Truck is loaded. Chassis, below that is wheel axle, and the load is transferred to the axle. The load is transferred to the wheel. The load is transferred to the wheel to ground, isn't it? Right? Therefore, load is transferred. Therefore, the section here, the section behaves like this. Section behaves. Sure? Do you agree? The section behaves when the load is transferred laterally, isn't it? Load is applied like this, and the load is transferred to the support, isn't it? Right now, through this member, horizontal member, the load is transferred to the support, isn't it? The load is transferred to the support, isn't it? When the load is transferred, the section, the arranged sections are behaving. When the load is transferred, no? The arranged sections are behaving like this. Do you agree? If you apply the force like this behaves like this. If you apply the force like this behaves, isn't it? If you apply the force in this direction, if you apply the force, this will become like this. If you apply the force in this direction, it becomes. Do you agree with me? Right? Got it? This beam is made out of number of sections. All these sections are arranged in a regular fashion, isn't it? In one fashion, you are arranged according to your convenience, isn't it? Understood? When the load is applied on this load is transferred to the support, isn't it? The sections behave depending upon the application of your. If you apply the more force, what is going to happen? More deformation. If you apply the less force, less deformation. Understood? Therefore, if the depth is more, what is going to happen? It resists more. You have seen your house rafters, roof, pakkas, manedu. Nodidira rafters. Have you seen the rafters? How they have kept it? Are they kept it like this? No, it is kept like this, isn't it? Because it resists the more force. The old people knows about our engineering, isn't it? Understood? Much better. Got it? And they were practicing it. Now therefore, now please understand the shape also contributes in resisting the force. Shape is also a major contribution in resisting the force. Understood? Isn't it? Depending upon, see, that is why if you keep the, if you apply the load like this, it deforms more. If you apply the force in this direction, it deforms more because the section is less. If you keep the member like this and apply the force, deformation will be because the section, isn't it? The section behavior, sectional behavior. How do you calculate it? Now, for example, now see, this is, let us consider this is one section, right? This section, you know, the beam section. This is one beam section, rectangular section. This has x-axis, this has y-axis, this has z-axis, three axes, right? X-axis, this is x-axis. The depth is more. X-axis, y-axis. Along the x-axis, depth is, along the y-axis, less, isn't it? Understood? Got it? When you apply the force here, then the length will be more, it resists more force, isn't it? Now this is less in this direction. X direction, the width is less. When you apply the force, isn't it? Understood? When you apply the force, now if you apply the force, less, isn't it? Less deformation. X-axis, y-axis, and z-axis. Understood? If you apply, if you are calculating in this direction, it is more stronger. Beam. This beam is more stronger in this direction now, isn't it? Now see, we'll consider this. This is the section. X-axis, more stronger, isn't it? X-axis, more stronger. Y-axis, less stronger. Z-axis, much more. Understood? The shape, isn't it? This we are defining in terms of moment of inertia. Understood? Got it? Isn't it? Now, shape contributes much more in resisting the force. Isn't it? Now you know that if you keep the wood, to resist the force, isn't it? If you keep the wood to resist, as a beam, it takes less force, isn't it? If you keep the steel, it resists the more, isn't it? If you keep the RCC beam, it resists, isn't it? Now depending upon their strength, it will carry, it will resist. At the same time, the same material behaves in different manner if the shape is different, isn't it? Do you agree with this? Got it? Now this shape, now strictly speaking, now we are deciding how we should keep this. If you know all these things, if you know the stress and strain, if you know how to calculate centroid, if you know how to calculate the moment of inertia, then you are able to calculate or able to fix, decide what should be the size of the wheel axle. What should be the size of the wheel axle? Have you seen the wheel axle? Isn't it? Have you seen the beam in the building? Right? The beams in the building, the depth, can we make it little bigger? Is it possible? Can we make it bigger? No, we can do it. What is going to happen if you make much bigger? It becomes waste, isn't it? If you make more stronger beam, it becomes waste. If you make the beam less size, less depth, then resistance will be, isn't it, less. There may be failure. See, if you design a beam, isn't it? If you manufacture the bigger one, it may become waste. If you manufacture the smaller one, it may become waste because of the less resistance, isn't it? Or if you make the bigger, it may become the waste because of the over resistance. Then who has to say how much it should be? It should be how much? The wheel axle you have seen, right now. There is a size, definite size for the wheel axle. If there is a definite size, who has said this should be like this? Engineer, isn't it? Engineers told they have decided what should be the size of the wheel axle. What should be the beam size? It is told by whom? Engineer. How come you know that? No, he has understood moment of inertia, then stress, strain, and its behavior. Therefore, he is able to decide much better sections, isn't it? Much better section. There should not be wastage. There should not be failure. Then you have to fix the material in such a way that it should do its job, isn't it? It should not be more than what is required, or it should not be less than what it is required, isn't it? Who has to decide? That is what we are doing here. We are learning here. Understood? Got it? The relevance of moment of inertia have understood? Isn't it? Once again I will tell you, no, this is the section. Isn't it? Section, you know. This is the section of the load resisting member, isn't it? Load resisting member, isn't it? Section. See, this has y axis, this has x axis, and also it has z axis. Along the x axis, it is much more because one more section is here. One more section is here, isn't it? Then it is y axis. Now, if you apply the force in this direction, the depth will be less. Therefore, what happens? Rotation will be earlier, isn't it? Understood? Got it? If you apply this is the z axis, much more strong. That is why columns are placed, isn't it? Down directly. Columns are placed, isn't it? Maybe wooden, maybe steel, maybe concrete, whatever maybe. Understand? Right? Do you agree with this? Moment of inertia, relevance of moment of inertia. It is a shape factor. It decides what is the strength, isn't it? To some extent, it contributes a very big contribution towards resisting the forces, isn't it? You have to decide which material, which shape is the best, isn't it? Depending upon the convenience, isn't it? Necessity, depending upon. That is why, see, now for example, how to calculate this, how to handle this, x-axis, y-axis, z-axis, okay? Now see, the moment of inertia, it is the secondary moment of the figure, second moment. How do you calculate it? See, again, the reference, most important, reference. See, for example, section, x-axis, isn't it? How it behaves with respect to this x-axis. The section behaves how with respect to x-axis. The same axis we can bring it here, another reference axis. The same section how it behaves with respect to. Isn't it? Understood? Reference with respect to reference. With respect to reference. With respect to which reference? Y axis. Some other axis which is parallel to y axis. Some other axis somewhere. Isn't it? How it behaves with respect to x. Now therefore this is the section. This section. This is an axis. Isn't it? Reference axis, not x axis. X centroidal axis, y centroidal axis, isn't it? Z centroidal axis, isn't it? Now see, now here, now this is one reference. This is the section figure. This is the reference axis given. How do you calculate the moment of inertia of this figure? What how it behaves? Isn't it? Now therefore, area of the figure A. Now therefore, moment of inertia can be calculated with respect to, see this figure with respect to IAB. IAB is the moment of inertia. I is the moment of inertia of the figure. IAB is the moment of inertia of the figure about this reference AB. Okay, got it? Now we go ahead. Right? Yeah, okay. Now, similarly, the moment of inertia I is equal to, if any given section, any given section, moment of inertia is equal to area into distance squared. Distance to the center. I told you already. I told you no. The center where we are applying the force, isn't it? How it behaves with respect to the reference axis, isn't it? Now, therefore, moment of inertia can be calculated with I, isn't it? Now, therefore, this is the radius. See, if you transform this, yeah, moment of inertia is equal to area into r square. R is the perpendicular distance from the centroid to the reference axis, isn't it? From the centroid to the reference axis, isn't it? So therefore, R is equal to under root I by A. It is called radius of gyration. Radius. Now, for example, this is the reference. This is the section. How it behaves. The radius. This is the radius, isn't it? Now, the radius of gyration. If you apply the force, that's why we will call this as radius of gyration, isn't it? Now, therefore, now let us see the unit of this is, please remember this, millimeter to the power of 4. So, millimeter to the power of 4 for what? For moment of inertia. Remember this. Now, our diploma students are lagging in rating the units. It is very, very, very important in each and every rating for all subjects. You must mention that simply we can't say 80. You must abbreviate always 80 millimeter. You must say always 20 millimeter. You must say always Newton. You must say always area millimeter square. You must say always kilonewton. Don't simply 80. What is answer? 80. What is 80? No, you must say always 80 millimeter square, 8 kilonewton, 80 millimeter distance, isn't it? Volume millimeter cube. You must mention it, isn't it? You must write it down. Everywhere, wherever you go, if that fellow should not ask the person who is opposite to you. If you say 80, what is 80? You should not. You must say 18 millimeter, isn't it? Then you never ask the next question. Burden will be reduced, isn't it? Got it? Okay. See, now this is the second moment of inertia. Now already I have explained this in general. In general, I have explained. Now with respect to the x-axis and the theoretical aspect, I will explain. I will say. Now, what is it? How do you calculate the moment of inertia? Now, always see, this is the section. See, figure, plain figure. This is the plain figure having area A. Plain figure having area A. Isn't it? Now, these are the axis, reference axis. X axis, Y axis, and Z axis. Isn't it? The figure is lying somewhere here. Now, for example, see, this is one X axis, this is one Y axis, and the corner is Z axis, isn't it? Now the figure is somewhere here. The figure is somewhere here, isn't it? The figure. X axis, one is X axis, the Y axis. Now see like this. This is X axis, this is Y axis, and this is the Z axis. This figure, how it behaves with respect to this axis, with respect to Z axis, with respect to Y axis, with respect to X axis. How this figure behaves, isn't it? That is what I have written here. X axis, Y axis, Z axis. And there is a figure. With respect to all these things, how it behaves, isn't it? Now, see, this is X axis. See, from here to here it is X distance. Centroid. The figure has the centroid. The centroid, Y axis, with respect to Y axis, at what distance the centroid? Centroid is lying at a distance X from Y axis. Isn't it? Centroid of the given figure is lying at a distance Y from X axis. Isn't it? Centroid is lying at a distance Z from Z axis. Do you agree with this? Isn't it? Any figure you take, any section, any plane figure, That is one centroidal axis. Now is it centroidal axis? Centroidal axis. Is it centroidal? No, this is not the centroidal axis. X, Y, Z are the reference axis. Isn't it? X, Y, Z are the reference axis. Centroidal axis are centroidal axis. X, X centroidal axis. Okay. Y, Y centroidal axis. Z, Z is the centroidal axis of the figure. Isn't it? Please note the difference. X, Y, Z. X. This is X. X is X, X. X, X is the reference axis. Y, Y is the reference axis. Z, Z is the reference axis. X, X. Centroidal axis of the given figure. Isn't it? Y, Y is the centroidal axis of the given figure. Z, Z is the centroidal of the given figure. Please make the difference. Isn't it? No doubt the difference. Understood? Now, see, if you consider like this, with respect to this figure, the moment of inertia of the given figure about x-axis centroidal axis is equal to ix. I, capital I, always referred for moment of inertia. I is always referred for, isn't it? Understand? Ix is the moment of inertia of the given figure about x-axis, centroidal x-axis of the given figure. Isn't it? Understood? Ix. Now this is the x-axis. When this is the x-axis, what is the moment of inertia of the figure? Area into distance square. Isn't it? Area into distance square. X-axis. Moment of inertia of the given figure about x-axis is equal to area into perpendicular distance. Isn't it? Distance square. So this is what we have Ix. Right? Moment of inertia of this figure about x axis is equal to area into y square. This is what I am. Similarly, this is moment of inertia of the given figure about y axis is equal to area into. Understood? So similarly, z axis with respect. Understood? Got it? Then we will discuss again day after tomorrow. We have one more class day after tomorrow. Now in that class we will continue and we will continue this and we will solve few more problems. Isn't it? With respect to the moment of inertia. Isn't it? We will solve few more problems, 2-3 problems. Isn't it? Now please understand now these things. Now we have discussed, we have highlighted the centroid, center of gravity and moment of inertia. Isn't it? Okay? Thank you very much. Thank you a lot. Thank you. Srinivas?